Hello learners, welcome back to my channel Shraddha's Physics. In this part we will see the expectation value. So let us start with the expectation value. Now if a system is in a state that is described by a normalized wave function psi, then the expected average or the expectation value of the result of the measurement of any observable q, it corresponds to the operator q cap, and that q cap it can be represented as, so this q cap will be equal to, that is q cap average, or this can be read as the expectation value of q, that is equal to integration from minus infinite to plus infinite psi star q cap psi d tau, and here this d tau represents the entire volume, and here the condition is psi is normalized, where psi is normalized. Okay, now we will see when psi is not normalized. For that is when the wave function is not normalized, then for that we can write this q cap will be equal to integration from minus infinite to plus infinite psi star q cap, this is your q cap psi, and here it is your d tau divided by integration from minus infinite to plus infinite psi star psi into d tau. Okay, and here psi is not normalized. When psi is not normalized, simply you have to divide that term. Okay, now here first of all we will see if the wave function, let me write, if the wave function psi, the wave function psi of the system is a normalized eigenfunction, so that eigenfunction, let me call it as psi I of the operator q cap, then we can write this q cap psi I, that is equal to lambda I into psi I, and here you know this lambda I is called the eigenvalue. Okay, so here this q cap operator can be written as the expectation value of this q cap is equal to integration from minus infinite to plus infinite psi I into q cap, that is psi I star into q cap psi I into d tau. Okay, and here when this q cap will operate on this psi I, then it will give the eigenvalue lambda I. So this will be integration from minus infinite to plus infinite psi I star, and here this will be lambda I psi I into d tau. Okay, or if I will take this lambda I out of the integration, then this will be minus infinite to plus infinite psi I star into psi I d tau. And here, since the wave function is normalized, since psi I is normalized, so we can consider this to be 1. Okay, that is this total integration is your 1. So that will be equal to lambda I. That is the expectation value of this q cap operator will be equal to lambda I, or the eigenvalue when the wave function is normalized. Okay, now the next we will see. So here let us see the expectation value of the position in the coordinate space. So first of all, let me write the, when the function is normalized, for that we are calculating here. So this is your x equal to, when the function is normalized, that is the psi is normalized, so for that the x average will be equal to integration from minus infinite to plus infinite psi star x cap psi d tau. Sorry, this is your dx. Okay, so this is your dx, and that is equal to integration from minus infinite to plus infinite psi star, and you know when this coordinate, that is your x cap, will operate on the psi, that is the position, x cap will operate on the psi, then it will give the eigenvalue simply x and it will be psi into dx. Okay, and here this is equal to integration from minus infinite to plus infinite. Here it is x and psi into psi star, that will be mod psi square into dx, and this mod psi square is nothing but the probability, that is the rho, and this can be written as equal to, this is integration from minus infinite to plus infinite x rho dx. Here let me write where rho equal to modulus of psi square, and that is called the probability, and this is called the probability. Okay, and similarly when the psi is not normalized, when the psi is not normalized, so for that we can write the expectation value of x will be equal to simply integration psi star. Let me write, this is your r. Okay, this is your r actually. Let me write in the three-dimensional system, this is your r equal to psi star r cap psi d tau divided by integration psi star psi d tau. This is in the three-dimensional system. If it is in one dimension, this is simply x expectation equal to psi star x cap psi dx divided by integration psi star psi dx, and the condition is the psi is not normalized. Okay, now the next is the expectation value of the momentum in the coordinate space. Okay, so now let me write first, this is your px cap average or the expectation value, that is equal to, let me write clearly first, this is your px cap average, that is the linear momentum operator, equal to integration minus infinite to plus infinite psi star px cap psi dx when psi is normalized. So here psi is normalized. Okay, it is normalized, and that is equal to integration minus infinite to plus infinite. Here this will be psi star, and in place of px cap I can write the operator value, that is equal to h cot divided by I, h cot divided by iota into dou by dou x and the psi dou psi by dou x whole into dx. Okay, and we can represent in the three-dimensional system, or we can say when the psi is not normalized. So for that p expectation will be equal to, this is your p cap expectation, integration from psi star integration over psi star h cot by I, this is your del psi d tau divided by integration psi star psi d tau. Okay, this is the condition when psi is not normalized. Psi is not normalized. Okay, now the next we will see the expectation value of the potential energy. So this is simply can be written as V expectation, that is equal to integration psi star V psi dV. Okay, now the next we will see the expectation value of the kinetic energy. Okay, so now for this if I write the Tx cap expectation, that is Tx average, that is equal to integration psi star T cap psi dx divided by, this is your integration psi star psi dx, and here this is your Tx cap. So for that I will write, this is equal to integration psi star, in place of T cap I will write, this is your Px square divided by 2m into psi dx divided by integration psi star psi dx, and you know the value of the Px equal to minus IH cot, let me write Px cap equal to minus IH cot dou by dou x, this is the Px cap operator value. So if I will put this value here, this will be equal to integration over integration psi star and here 1 by 2m is present. So px cap will be minus square is plus 1, I square will be minus, so that will be minus h cot square divided by 2m into dou square psi by dou x square whole into dx, and it will be divided by integration psi star psi dx. Okay, and here when psi is not normalized, this is the condition, but when psi is normalized, for that we will write t expectation will be equal to integration psi star minus h cot square by 2m. That is in case of the 3-dimensional system. If I write for this case, let me write it first. So here in case of the 3-dimensional system, we can simply write this t expectation equal to integration psi star, this will be minus h cot square by 2m into delta square psi dx divided by integration psi star psi dx. So here also we can write simply minus h cot square by 2m, this is your delta square psi whole into theta. Okay, sorry, let me write it as theta. This is theta and it is also theta. Okay, that is in the 3-dimensional system. Here I am representing. So here the difference between the two is, here the psi is not normalized, but here the psi is the normalized one. And similarly, you can calculate the expectation value of the angular momentum operator also. For any operator, you can calculate now the expectation value. Simply you have to check whether the function is first normalized or not. That after you can calculate. So here you can see, in the previous lecture we have already discussed about this angular momentum operator. So from this part, that is you know the Lx cap operator, that is Ly operator, and also the Lz cap operator, or simply this L cap operator. So from this expression also you can calculate the expectation value of this angular momentum operator. Okay, so this is all for today. If you have any doubt, can ask me in the comment section. Thank you all.